Hello again. The last time we have talked about the random variable concept, and we have classified the random variables into two classes, discrete random variables and continuous random variables. A discrete random variable can take a countable number of possible real values, and they can be modeled with probability mass functions. However, a continuous random variable can take an uncountably many possible values, and they can be modeled according to their probability density functions. Today, we are going to learn about some spatial discrete random variables which can be used to model real-life probability questions. The first of these spatial discrete random variables is a Bernoulli random variable. It is the simplest of these discrete random variables, and it is going to provide us a basis for learning the other discrete random variables, such as binomial random variable, Poisson random variable, and the geometric random variable. Additional to those, we are also going to learn about the negative binomial random variable and the hypergeometric random variable. And these lists, the list of the spatial discrete random variables, we can say that all of these random variables can be classified according to their probability mass functions as they have a spatial construction. So let's start with the Bernoulli random variable. Consider a random experiment whose outcome can be classified as either a success or a failure. So as an example, we can give a penalty shot. So if the penalty shot is scored, then we say this is a success, or the penalty shot cannot be scored, and this becomes a failure. Okay? So such experiments, which have only two possible outcomes, are called the Bernoulli experiments. Now, on the sample space of these random experiments, we can define a random variable denoted by capital X. And if the experiment ends up with a success, then this random variable takes a value of 1. And if this random experiment ends up with a failure, then the value of the random variable will be 0. In that case, this becomes a discrete random variable, which can take either of the two possible values, a 0 or 1, okay? And if we say that the random experiment ends up with a success with probability p, where p can be any value between 0 and 1, including the boundaries, in that case, the random variable x follows this probability mass function, which means the random variable takes the value of x. If x is equal to 1, the random variable takes the value of 1 with probability p. And the random variable x takes the value of 0 with probability 1 minus p, where p and 1 minus p are respectively the success and the failure probabilities of the Bernoulli experiment. Because the Bernoulli random variable can take either of these two possible values, the probability mass values at anywhere else over the real line are simply 0. And then we say that this capital X is a Bernoulli random variable with success probability P. So with different values of success probabilities, with different values of P, we get a different Bernoulli random variable. And given the structure, we can calculate the expected value and the variance of a Bernoulli random variable. Remember now, for discrete random variables, the expected value of that random variable is calculated by multiplying the possible values that it can take with the corresponding probability mass values, and all these values are summed up. In that case, for a Bernoulli random variable, 1 must be multiplied with the success probability and 0 must be multiplied with the failure probability. And the expected value of a Bernoulli random variable with success probability P will be equal to its success probability P. And the variance of the random variable can be calculated by the convenient formula here, expected value of x squared minus square of the expectation. The expected value is already calculated as P. Therefore, we need to calculate the expected value of x square, which means we need to multiply 1 square with P and 0 square with 1 minus P. Hence, the expected value of x square will also be equal to P. And this difference, expected value of x square minus square of the expectation, will simply be P minus P square. And as P is a common multiplier here, we can summarize this as P times 1 minus P. Now, let's practice the Bernoulli random variable over a question. Suppose we are playing a game in which we will be winning $1 with 0.15 probability and no money with the remaining probability. Now, before moving further, let's just say the outcome of this game is either 0 or 1 according to the amount of winning. Therefore, the amount of winning in this game can be modeled by a Bernoulli random variable where the success probability is equal to 0.15. The question is asking the following. It says, write down the probability mass function for the amount of money that we will be winning. And we also need to find the expected amount of money that we will be winning and the variance of the amount of money that we will be winning. Now, we know that the game ends up with a success or a winning situation with probability 0.15. Therefore, X conforms the properties of a Bernoulli random variable with success probability 0.15. And the probability mass function, or in other words, the probability of this random variable to be equal to different X values over the real line, can be described accordingly. So if this lowercase x is equal to 1, then the probability of my random variable being equal to 1 is 0.15. And if this lowercase x is equal to 0, then the probability of my random variable being equal to 0 is 0.85. And the remaining probabilities for other values other than 0 and 1 are simply 0. And the expected value of such Bernoulli random variable is simply equal to its success probability, and the success probability is 0.15. And the variance of a Bernoulli random variable is calculated according to the formulation, P times 1 minus P. And since P is 0.15, we can plug in the values. Hence, the variance of this Bernoulli random variable is 0.1275. Now let us solve another question. We consider a game in each round of which we may win a $5 with a small probability P or nothing with the remaining probability. Now this question is emphasizing two things. The amount of winning in the end of a round of this game is either 0 or 5. Therefore, it does not exactly conform the properties of a Bernoulli random variable. Remember, a Bernoulli random variable can only take a 0 or 1 value. The question also emphasizes that in this game, we can win a $5 with a small probability. Okay? And on the other hand, we cannot win anything if the outcome is 1 minus P. If the variance of a round's winning is 1.1875, the question is asking the P value. So P is unknown. The success probability here is unknown, but what we know is the variance of the rounds winning. Therefore, we need to model the rounds winning. Now, we are going to utilize the help of a Bernoulli random variable here. Let us start by modeling the winning status of a round. Okay, so before modeling the outcome as the amount of winning, let's just model the status of winning. So the winning status can either be 0 or 1. This means if we lose the round, then the winning status will be 0. If we win the round, then the winning status will be 1. Therefore, if we define capital X as a Bernoulli random variable, it takes 1 value if we win and it takes 0 value if we lose. and the probability of winning is P. Therefore, X is a Bernoulli random variable with probability, success probability P. And we can also model the amount of winning in the end of a round as 5 times X, because if we lose the round, the winning status will be 0, and the amount of winning will be 5 times 0 equal to $0. If the winning status is equal to 1, then this means we win, and 5 times 1 will become $5, exactly the amount of money that we are going to win. Therefore, the question provides us the variance of a round's winning is 1.1875, and the variance of 5x should be equal to 1.1875. Now, we know that if there is a linear transformation applied over a random variable and we calculate the variance of that linear transformation, the coefficient in front of the random variable gets out of the variance as squared. Therefore, variance of 5x will be equal to 25 times variance x. And the variance of a Bernoulli random variable is equal to p times 1 minus p, or in other words, p minus p squared. And this value should be equal to 1.1875, as this information is provided by the question. Now, here we have a quadratic function or a second order polynomial, and it can be transformed into this form. And the roots of this quadratic equation can be found by using the discriminants and the coefficients of the first order and the second order term. The roots will be calculated as 0.05 and 0.95. However, only one of these results is our answer. The question especially emphasizes that the success probability or the probability of winning is small. Therefore, we favor P to be equal to 0.05 as the answer of this question.